The topic of this lecture is diffusion of solids into one another. So far, we've already covered basically what diffusion is, especially on an atomic level, what affects it, namely temperature and the type of host material, and the type of diffusing material, and also what kind of positions, if it's in some type of crystal lattice, if it's substitutional or interstitial. We also covered flux, and that's what this J here stands for, is that the flux is proportional to the concentration gradient. So if there's more on one side, less on another, you'll have a higher gradient, which will give you a greater difference here and lead to a higher flux, J. Now what's very important in this equation is this right here, the diffusion coefficient. The diffusion coefficient has its own equation associated with it. So we're going to dive into that next. How do we find this all-important diffusion coefficient? This diffusion coefficient is where we find the dependencies on temperature and the materials and so on. We assume that if first law of diffusion is linear, that this derivative here is simply a difference from one concentration to the next over the distance involved. We can sometimes assume this, although it's fairly simplistic. Now here's our diffusion coefficient, D. It is equal to d naught, a pre-exponential. This is referred to as the pre-exponential, and this is dependent on the materials involved. But then we take that pre-exponential and we multiply it by e raised to the power of negative qd over RT. Well, qd is the activation energy that's also highly dependent on the materials involved. The gas constant, which is again a constant, so at least that's the same. Notice the units that we have here, joules per mole Kelvin. Here this could be joules per mole, or sometimes it's kilojoules, so you got to watch out for that. And T is the absolute temperature in kelvins, so might have to make some conversions there. This temperature dependence is actually exponential. If you want to get a good idea of what this graph means, start up here. Notice how our temperature is going down from left to right. So start up at 1500 and then we go down to 300. But it's not linear. What's linear is this scale, where we have 1000 kelvins divided by our temperature. So of course, 1500, 1000 K divided by T, well, this would actually be adding 273. This would be about 1773 degrees C, and that 1000 divided by that will be a little more than a half. And this area is linear. So these are actually, although they look like they're negative slopes, they're positive slopes. So going from right to left in increasing temperature, we also have an increasing diffusion coefficient. And notice that this scale is not linear. It is also logarithmic. So as it moves up the scale, we're going up by factors of 10. So it's highly dependent on temperature. Notice also that these two are carbon in iron. They have a much higher diffusion coefficient than these other ones that are substitutional. And that's to be expected because there are many, many interstitial sites compared to substitutional sites to diffuse through. I took this chart and I turned it around. This one should be in your book somewhere. And I turned it around so that you could see the positive relationship between temperature here and up above, or the reciprocal temperature here, and the increasing diffusion coefficient. And you see these two as well as a couple of others. This is a very important graph for the explaining why we use aluminum in silicon chips rather than copper or gold or silver. Well, obviously gold and silver are very expensive, so we might not want to use those just for cost's sake, but they have very, very good electrical properties, especially low resistivity. So does copper. That's why we use a lot of copper wires in houses. But copper diffuses very easily in silicon. So it has a very high diffusion coefficient even when the temperature isn't all that warm, in the 400 or 500 degrees Celsius range. But aluminum, on the other hand, does not diffuse very much. So this is, the aluminum diffuses at 500 C at 2.5 times 10 to the negative 21st meters squared per second, whereas the copper is 10 to the 8th times that. So when you're talking about these types of temperatures in silicon, in say a computer, the copper is much more likely to diffuse further into the silicon, causing problems in the circuits, whereas aluminum is much more likely to stay put. So we have an example here. At 300 degrees C, the diffusion coefficient and activation energy for copper in silicon are such. What is the diffusion coefficient at 350 C? Well, I'm going to show you two ways of solving this problem using mathematically sound ways. One I would prefer, the other one I find is more confusing. So we'll start with the more confusing one, is to take this data and transform it into linear data. Well, we have two equations here. The equation for D2, which is 350 C, and the equation for D1 at 300 C. So it's temperature 1 is 300, temperature 2 is 350. Well, what's common with both of these? Well, we have R is a gas constant, it's the same. QD is the same for both of these as well. The temperatures are different, but we know what those are. Thing is, we don't know D naught, the pre-exponential, and we don't know the diffusion coefficient, which is our ultimate goal here. Well, this pre-exponential should be the same, and we'll use that later. The next step is to set these up so that we simply take one linear equation and subtract it from the other one. So this minus this is the same thing as natural log of D2 minus natural log of D1, which is right here, but using the properties of the natural logs, we can say that that's also the natural log of D2 over D1. And since these expressions both have natural log of the pre-exponential, and we're subtracting them from each other, that term is deleted. The negative QD over R is the same for both, so we end up with this expression. What we're going to do is we're going to take E and raise it to the power of both sides of these equations. So that's to get rid of the natural log. And then we multiply through by D1, and we end up with this expression. So now we have a full expression that we can just plug numbers into for our diffusion coefficient for our second temperature, 350 C. And we plug in these numbers in, and we end up with D2 equals this. Now, I have a second way of doing this, which will get us the same answer. And instead, I want to solve for this pre-exponential. So I'm going to use just the first equation first, and then use the equation again with the second temperature next. This way, we will take D in this equation here, and we're going to rearrange it. So basically divide through by this term, both sides. And if you're dividing by something to a negative power, that's the same thing as multiplying it without the negative power. So this D naught, the pre-exponential, is equal to D times e to the QD over KT. And I'm going to plug these numbers in, and we end up with a pre-exponential equal to this. Well, then we use this equation again for D at 350C. Now notice here and here are the different temperatures. Sometimes students make that mistake. But I'm going to use my pre-exponential value right here and multiply by e raised to the negative QD over KT using the second temperature, and I will end up with the same value as I had before. I find this method a little more straightforward, number one, and number two, we end up actually calculating the pre-exponential, so we could use that possibly at 450C very quickly. Fick's second law states that the concentration is a function of time and position. So you need to take a partial differential equation and solve it. By doing so, we end up with these types of curves for the concentration at different times. So that's at the initial time, that's at some time later, and some time later. This indicates that our concentration is higher at this point at the later time than this point at the earlier time, than this point at the earlier time. And at this point, at the initial time, there was no, or there was merely an initial concentration of copper atoms in this bar. In order to solve this differential equation, we end up with this equation. The concentration at a certain distance and time minus the initial concentration there, divided by the concentration at the surface. So remember, we're looking at a copper bar of aluminum, and so we're looking at the surface, and it could be, this just happens to be aluminum and copper, but it could be any surface that we initially bring a diffusing species into. So this is the concentration at the surface minus the original concentration in the bulk of the material is equal to 1 minus the error function of x, which is our distance into the material, over 2 times the square root of, here's our diffusion coefficient again, times time. Now, look at this here. This is unitless. We've got concentration on top, concentration on the bottom. This is simply a ratio. Is equal to this. Now, what is the ERF? ERF is the error function, and it can be looked up in a table like many other types of functions. You can look up cosine and sine and tangent. This is another function. This is the error function, and it is derived from this integral, but mostly we can use it either calculator sense or we can look it up in a table. Now I have a table right here, and this is from the Callister textbook. By the way, if you do not use the Callister textbook, please go buy it. It is an excellent textbook from J. Wiley and Sons. So the error function of z. Now, error function is used in many different applications, and all we need to do is find this z. Z is, for us, in this course, x over 2 square root of dt. So z is that, and we look it up in this table. Now, if it doesn't happen to be exactly 0.25, we need to use interpolation to find it. So, and then find its approximate value. And notice that we have 3 total columns here. So 0.25 results in an error function of 0.2763. Then this z column continues over here, and then over here again. So again, this graph indicates that the concentration at the surface is the maximum concentration we'll get on this curve. And if x is this distance from here to here, this distance from the interface x, then we have a concentration right here. That's what that line is. And the difference between that and the bulk concentration over here, C naught, is this Cx minus C naught, and the Cs minus C naught is this distance right here, the concentration at the surface versus the concentration in the original bulk. So we're going to have a sample problem with that. We have an iron carbon alloy with 0.2% weight percent carbon is carburized, and we want to put carbon into the surface to make it harder, perhaps. And we want a surface carbon concentration. We're going to hold it constant at 1.0 weight percent, and we're going to hold it for 49.5 hours. And below the surface, we measure that the concentration of carbon is 0.35 weight percent. And we want to figure out what temperature it was at. So we're going to use our error function here. Now we know several of these things. Cxt, well, x is the distance, t is the time. The concentration is 0.35%, and the distance x is 4 millimeters below the surface, and the time t is 49.5 hours. So we know that concentration, 0.35%. We know that the concentration at the surface is 1%, and the concentration in the bulk is 0.2%. So we know everything in this equation except d, the diffusion coefficient. So we're going to have to figure that out. So we plug this equation in here. As I said, we have all of these values. And we have a value here that is equal to 1 minus error function of z. So we know what this is going to end up with. Error function of z is going to be 0.8125. So we find that number here, 8125. Well, we don't have it on our chart, so we'll need to interpolate. Interpolation simply means that we're assuming that between these 2 points, our curve is approximately linear, close enough to do an approximation. So we set this up as a ratio. The ratio of the difference between these two and the difference between the top and the bottom must be equal to the ratio of the difference between these two and the difference of these two from top to bottom. So we take the difference here and the difference here, we set it equal to the difference here and the difference here, and we can find our z value. Then we set it equal to what we know as Z in our material science equation, and we solve for D. So for Z, we multiply it by 2, divide it by x, square it, multiply it by t, and then take the inverse. So doing some algebra, we end up with D equals this. And now we know everything here because we found out Z. And we end up with our diffusion coefficient. Well, that was tough, but we're not even done yet. Now we need to solve for the temperature T. So we plug it into our diffusion coefficient equation, and solving for that, we need to also know the QD and the pre-exponential, but we can look that up in table 6.2. And we can calculate our temperature. Before I go to the last step to actually find our temperature, note that the diffusion of carbon in FCC iron is different than BCC iron, which is different than several things. You should look at that table very carefully and figure out how it works. If this is the diffusing species, this is what's going into a host metal. So this is iron into alpha iron. And alpha iron is at different temperatures, so it's only is between these temperatures, whereas gamma iron is between these temperatures. So we have our pre-exponential here, our activation energy QD here. We can use either one of these as long as we keep our units straight. And we even have a calculated value for these various temperatures. And this is, again, iron into iron. Now here we have carbon into iron and carbon into iron, and notice how our pre-exponential has changed significantly compared to what we have up here, and our diffusion coefficient is very different for carbon into iron than iron into iron. It's much higher here because carbon is a much smaller atom and goes into interstitial sites rather than substitutional sites. So again, this is copper going into copper, zinc going into copper, aluminum and aluminum, and so on. And finally, we have our temperature equal to 1300 K, or 1027 degrees C. In summary, we have faster diffusion for more open crystal structures, materials that have secondary bonding such as polymers, for smaller diffusing atoms, lower density materials. But the diffusion is slower for close packed structures like HCP or FCC, materials with covalent bonding, and larger diffusing atoms and higher density materials.